Hello, math application students, and welcome to your online lesson. Today we'll be looking at rules of exponents and applying those exponent rules. We will know we are successful when we can efficiently solve IB level problems involving rules of exponents. Now, these rules of exponents are probably rules that you've seen before, so most of this might be review for you, but we'll also expand on this in upcoming lessons. So I've got three examples for us to start with right here, A, B, and C, and we want to use exponent laws or rules in order to sort of combine our exponents and simplify these expressions a little bit. We're not going to simplify to a final answer, but at least some sort of power. Speaking of power, let's talk about vocabulary a little bit before we jump into these. Here I have a power. 3 to the 5th power is how it's often read. And a power has two parts. One is the base. The base is the normal size number or variable that's being raised to our exponent. And then we have the exponent itself. And the exponent itself is a superscript, which means it's small and it's up high compared to a regular size number like our base. And what does an exponent do? An exponent is a shortcut that counts how many of our bases we have. So in our first example, at least in this first part here, we have a base of 3, an exponent of 5, so we have 5 3's. The exponent again counts how many bases. 5 3's getting multiplied. So a 3 times a 3 times another 3 times another 3 times another 3. So 5 3's getting multiplied together. And then you can see that we are multiplying by another 4 more 3's, or 3 to the 4th power. So times 3 times another 3 times another 3 times another 3. And altogether, what do we have? We should have 1, 2, 3, 4, 5, 6, 7, 8, 9 3's getting multiplied together. So 3 to the 9th power. Now you may remember from a previous math class, there is a shortcut or a rule or law that allows us to say when you have two powers getting multiplied and they have the same base, and in this case both of these have a base of 3, you can simply add the exponent. Well, when I add my exponents of a 5 and a 4, 5 plus 4 gives us 9, so we have 3 to the 9th power, which is the same thing we had there. Now if you ever forget the rule, you can always do it the long way like we started with. Just write out 5 3's for this first power and 4 3's for our next power, and then say how many 3's do we have getting multiplied, and that's what exponents do. They just count up how many of our bases are being multiplied. But if you know the rules, it makes it a little bit shorter. Let's look at the second example here. This time we're dividing. Well, if the rule previously said we could add when we are multiplying and the bases are the same, here we have 2 5's being divided, so with our exponents we should subtract. Okay, well if we subtract, we have a power of 3 and a power of 5. 3 minus 5 gives us -2. So our base is 5 to the -2nd. Well, this raises another question. What does it mean to have a negative exponent? Well, to better explain this, why don't we actually look at what this means when we expand all this out? So in the numerator, we had a 5 to the 3rd power. So that's 5 times 5 times 5, or 3 5's getting multiplied. In the denominator, we had 5 5's. 1, 2, 3, 4, 5. And now we're dividing. Well, I have a 5 in the numerator, and it's being divided by another 5 in the denominator here. And so we may remember from pre-algebra or arithmetic that 5 divided by 5 becomes 1, or they cancel out. And we see another pair of 5's dividing right here. They cancel out as well. And then another one canceling out. So what are we left with when we get all the way through this? Well, we just have 2 5's, but they're both in the denominator. So that would be like a 5 squared. 2 5's being multiplied, but they're in the denominator. What would be in the numerator? Well, all of our 5's canceled out. And remember, when things cancel out with multiplication and division, they become 1. Not 0, but 1. Adding and subtracting, things cancel to become 1. And so we'd have like a 1 times a 1 times a 1 in the numerator, also known as just 1. So looking back at our original shortcut answer, we had 5 to the -2nd. We should have had 1 over 5 to the 2nd. But these are the same thing, because a negative exponent, the negative tells us opposite, right? Like the opposite of having $5 if I had $5, but I didn't have it, let's say I owed it, that would be negative $5 that we have here. And so that negative $5, or the opposite of $5, owing it, is indicated by that negative sign. Well, what does an exponent do? We have a negative exponent here. It counts how many times we multiply. Well, the opposite, or the negative, of multiplying would be dividing. And how do you divide a 5? Well, we can just do the reciprocal, and that's what we have here. So our negative exponent allowed us to take our base and throw it into the denominator. We're doing the opposite. We're no longer multiplying those two 5s. We are now dividing them, and that's what a negative exponent does. Looking at our last example here, this time we have what we call a power of a power, where you have a single base with an exponent, and then all of that power essentially is being raised to another exponent. Again, we call it a power of a power. The difference between part C and part A had two bases that were the same. Both bases were a 3. Here we have just a single base, that base of m in part C here. Well, m to the 4th is being raised to the 3rd power. So we have 3 of those. So we have an m to the 4th, and then we have another m to the 4th, and then one more m to the 4th, or 3 m to the 4ths. And now it's a lot more like part A, where you have the same base, 1, 2, 3 of them, all getting multiplied. And so all we have to do is take our exponents, which was 4 for each one of these, and add those up. Well, 4 plus 4 plus 4 gives us 12, m to the 12th power. But you may remember there is a rule or shortcut for this as well. And that rule says we have a power of a power, and again, there's just a single base here. You can take those exponents that are getting applied to each other and simply multiply them. And 4 times 3 would get us right to this answer here of m to the 12th power. All right, let's formalize some of these examples. On this slide here, I've got all the different power rules or exponent rules or laws that we are going to be looking at in this lesson. The first several we've already talked about, so let's go through these. This might be a good slide to sort of pause and write some of these down. Actually, write all of these down, and I'll circle what I would want you to write down in your notes. These right here are the exponent rules that we need to know. So again, let's go through each of these. The first one is what we saw on the very first example we did. There's two bases that are the same, each getting raised to an exponent, so we simply add those exponents. The next one is like our second example. Again, two bases, they're the same here, both a, and so we subtract our exponents since the original powers were being divided. The third one was like our third example, where you have a power of a power, just a single base, one base with two exponents. And so we multiply those exponents together here. All right, now we're going to jump down to some slightly different things. These next two are essentially the same. In the first one, we have two different bases multiplying, and then we have those two bases being divided. And in both cases, they're being raised to a single exponent. But what we can do is we can distribute those exponents so that each of the numbers, or each of the bases, a and b, that we're getting multiplied, each get those exponents. Again, this only works for multiplying or dividing. It doesn't work for adding and subtracting. And then towards the bottom here, anything raised to a 0 power is 1. And we'll look at an example in a little bit that sort of explains why that's true. And then finally, we saw this also on the opening examples. When you have a negative exponent, that means do the opposite of multiplying. So we throw it into the denominator, essentially making a reciprocal and showing division. Again, make sure that you have those rules in your notes. Moving on. So here's another example where we are dealing with brackets or parentheses showing groups. So this is like that law on the previous slide, where you have multiple bases all being raised to a single exponent, which means we can distribute this exponent to each base. So it's going to go to the a, and it's going to go to the 3. But the, well, actually, let's work it through in order. There's also actually a negative here, and I want to talk about that for a quick moment. If we have a negative like a -1, times another negative, it becomes a positive. We'd have a +1. If we were to multiply a negative times another negative, that would become a -1 because the first two would cancel each other out, becoming a positive, but then we'd still have one extra negative right here, leaving it to a negative. Now what happens if we have 4 negatives? Well, that would be -1 times -1, which becomes positive. And then we'd have another -1 times a -1, which would also be positive. And then when you multiply those two positives, they will be positive as well. So we can sort of summarize to say that anytime you have an even exponent, multiple of 2, 2, 4, 6, 8, 10, so on and so forth, we know that the negative would become a positive. And anytime we have an odd exponent, that is going to keep it being a negative, because if you have a negative times a negative times one extra negative, those first two negatives will cancel out, but you'll still have a negative left behind. So on this first example, right away, we know that this negative here, since we're raising it to the 4th power, it's going to become positive. So our answer is going to be positive, and then we need to distribute this to the third, or the base of 3, and then also this a squared here. Well, 3 to the 4th power is what we'd have here, and then a was already being raised to the 2nd power. Now we essentially have a power of a power. So a squared being raised to the 4th power. Since it's just a single base of a, we are going to multiply those exponents. So we have a to the, 8th power here, 2 times 4. All right. Again, you could do this the long way. We could do a -3 times a -3 times a -3 times a -3, and then a squared times a squared times a squared times a squared, but we should end up with this. If you want to fully simplify this 3 to the 4th power, 3 times 3 is 9, times another 3 is 27, times one more gets us to 81. So 81 a to the 8th power. But I'm going to focus mostly on just looking at these exponent rules. All right, part B. Again, there's a negative. It's inside the parentheses. This time we have an odd exponent, so that means we are going to keep the negative. Even would cancel out any negatives. This time we're going to keep it, so we'll have a negative answer. All of our bases, we have a 2, an a, which is already being squared, and a b in the denominator. Well, 2 to the 3rd power is our first one, because we're distributing this 3 here again. A to the 2nd power, we already have a to the 2nd power. Now we're being raised to another power. We multiply those, so we'll have a to the 6th power. And then b was just like an implied 1 there, if you want to think of it that way. And so it's going to be b to the 3rd power here. If you want to simplify 2 to the 3rd power, that becomes 8. So we'd have negative 8a to the 6th all over b to the 3rd. That negative goes with this fraction that is our final answer. Sometimes people will write it as part of like going with the 8. It's fine as long as there's only one negative in our final answer. Let's look at another example. All right, we're going to write without negatives. Well, a reminder that if there's a negative, it's with an exponent, it's not making our base negative. All it's doing is telling us to do the opposite of multiplying. Well, this a to the 3rd power is negative already here. So the opposite of having 3 a's getting multiplied would be having those 3 a's getting divided. So we're simply going to throw it in the denominator. Again, the a to the 3rd power used to be negative. When I put it in the denominator, I make it positive. B to the 2nd, it's already positive, so it's going to stay put right where it was. C to the -1. Well, this one's negative, but it's already in the denominator. So again, we're going to flip it, do the opposite, the reciprocal, put it in the numerator. And I'm not going to write a +1 because a +1's already implied because there's just a single c there. Also, you'll notice that I wrote everything in alphabetical order. So I have the b squared followed by the c, and then the a cubed is in the denominator. All right, let's talk about things to the 0 power. Well, we already looked at a rule that said anything to the 0 power equals 1. So let's talk about why that is. So let's look at part B. In part B, we know from our shortcut rule that we could, since the bases are the same, they're both x, we could take our powers and subtract them. 3 minus 3 gives us x to the 0. We also know that if we were to expand this, we'd have x times x divided by x times x times x. And what is any number divided by itself? X divided by x would become 1. And we have another x divided by x becoming 1, and another x divided by x becoming 1. And 1 times 1 times 1 times 1 equals 1. So if x to the third divided by x to the third is 1, and we know from our rules that x to the third divided by x to the third is x to the 0, then we know that x to the 0 must also equal 1. The only thing I want to remind you here is that parentheses are important. We've looked at this throughout the year, but the only thing being raised to the second power in part A is the x. So we have an x squared, and then we have a negative in front of it. So it's a negative x squared. If x were 3, that would be like 3 squared with a negative in front of it. 3 squared is 9, so it's negative 9. Part B, on the other hand, is saying the negative is also being squared because of these parentheses that we have here. And so we have a negative times another negative because it's being squared. Let's call it like a negative 1 because there's technically like a coefficient of 1 there. So you'd have a negative 1 times a negative 1. Again, 2 of them because we're squaring. And then we'd have that times this x times another x. So we have a negative times a negative, which becomes positive, and then you have an x times an x, which becomes x squared. And if we were to put a number in for that, like we did previously where we let x equal 3, that would just become positive 9. So the parentheses make a difference. On the original one, we had x, negative x squared, and once we put parentheses around that negative x, the actual simplified value is a positive x squared. Last example for this video here, just a real quick simplification one. It looks big, it looks complicated, but we're just going to use our rules. There's no like terms in the numerator or the denominator. We have a 4, an x, a y, and a z. In the denominator, we have a 3, an x, and a y, and a z as well. So we're dividing all of these things. We have a 4 divided by a 3, which doesn't come out to a nice number, so I'll leave it as a fraction. X to the 5th divided by x squared. Subtract those exponents. So we have x to the 3rd power. It's positive, so I'm going to put it in the numerator. Then I would have y to the negative 3rd divided by y to the negative 4th. Well, negative 3 minus a negative 4, two negatives make it a positive, so I'd have negative 3 plus 4, which equals 1. So that's just one positive y. Since it was positive, again, we're going to put it in the numerator. For the z's, we have, let me clean this up just a little bit. We have a z to the 2nd divided by z to the 6th. We are going to subtract those. 2 minus 6 gives us negative 4. Now we could write z to the negative 4th right here, but since it's negative, where is it ultimately going to go? Into the denominator, and so we would have a z to the 4th power. I don't write the negative. Instead, I simply throw it into the denominator, and that would be our final answer. 4x to the 3rd power y divided by 3z to the 4th power. And that is where we're going to finish up for today. So till next time.